Good morning, my dear students. Last session we have discussed about the three-hinged arches, um, the definition of three-hinged arch, and then types of arches, and some of the pictures that the real arches, how they look like. And then we have moved on to the uh, theoretical arch definition, its construction. That's what happened in the last sessions. Today, let's see in this session the theorem that the actual arch uh, and the theoretical arch, the theorem that relates these two, we will see now. Okay, that is what is called EDDY's theorem. What exactly this theorem do is, the other way I can say, it relates theoretical arch and the actual arch. Okay, what is meant by theoretical arch? What is meant by actual arch? A theoretical arch is the one wherein only compressive force uh, exists in the arch, whereas actual arch means the arch which you construct uh, in reality, in the field. That is where the bending moment also present in it. The reason behind that, you can't construct a theoretical arch for a given load case, because the shape of the arch, funicular shape of the arch, depends on the type of load that you apply. So practically, the load comes on the arch is different. Many of the loads, multiple load cases may be there. You can't have a single load type, like there should be a point load only, or there should be UDL only. You can't have such restrictions practically. So the theoretical arch it cannot be constructed practically, whereas actual arch is the one which you construct, which will have bending moment also along with the compressive force in the arch. This is what is clear difference between what is theoretical arch and what is actual arch. And this theorem, what we are going to study now, this theorem, what is called EDDY's theorem, that we are going to see it now, will relate the theoretical arch and actual arch. Let's see next what is a theorem, and how you prove the theorem, and what exactly this is. So this, let's see statement first. This is the statement. Bending moment at any point on the arch, which means actual arch. That means this one, this blue line, uh, which is the actual arch. So bending moment at any point on the arch axis is proportional to the vertical intercept between theoretical and actual arch. So whereas theoretical arch here is the network of lines drawn here. This is the theoretical arch. As I said, theoretical arch is nothing but the arch which has only compressive force in the arch. The only compressive force develops in it. So that we have seen in the earlier class, that how to construct this theoretical arch. That is what we call the elastic theory of arches that we have studied in the earlier sessions. Okay, so this is the theoretical arch that you see with the network of lines, nothing but you can see the portion PS is a line which indicates a certain compressive force value. Similarly, the portion ST is the line which indicates certain compressive force. How do you get these values? Compressive force values uh, is by constructing theoretical arch from the procedure we have seen earlier, and the value is nothing but the scale that you have already taken for drawing it. It is by graphical procedure that you have constructed this by taking some scale. So maybe one centimeter is 10 newtons or something. So that scale, what you have drawn there, that you measure it here, you get in terms of centimeters or something, that you convert to newtons by the scale that you have chosen. That will give you the value of compressive force acting in this portion, similarly in this portion, similarly in this portion, similarly in this portion, likewise. So these are all the lines that represent the different compressive force values in those portions. So that is what is the theoretical arch. This is explained earlier clearly. Now let us see once again the statement. The bending moment at any point. So the point chosen here is the point A, and corresponding point on the actual arch is this one. This is the actual the point selected on actual arch, corresponding point. You may name it as some say A dash. Okay, A being the point on theoretical arch, A dash being the point on actual arch. So bending moment at any point, that means A dash, on the arch axis, which means actual arch, is proportional to the vertical intercept between theoretical and actual arch. This is what is the vertical intercept, that is denoted by letter small e. So what does this statement means? Bending moment at this point is proportional to the distance between these two arches, that means E. So bending moment is proportional to E. Similarly, if you pick this point, the bending moment will be proportional to this height, I mean vertical different vertical intercept. Similarly, at this point, this is the value. So you can clearly identify how the bending moment in the actual arch is. You can see bending moment is 0, then it is going on increasing, then reduced. Likewise, you can have a clear picture of bending moment value qualitatively, not the quantitative value. Qualitatively, you can identify where is the maximum bending moment or the region where maximum bending moment is, and the region where the minimum bending moment is. Likewise, you can have a clear picture of bending moment developed in this arch. This is what is the use of this theorem, EDDY's theorem, which will give you qualitative idea of bending moment in actual arch. Let's see how do you prove this theorem. Okay, so let me clear whatever is drawn there for having a clear picture of that. Right, so let PQR is actual arch, that is what is this one, PQR, and Q being the crown point, P and R are the springing points. So let PQR is actual arch, and PSTUVR, all these points I have listed out here. The points on theoretical arch is funicular polygon, the other name for theoretical arch, representing theoretical arch. So funicular polygon, right? Then select a point A on line of thrust. This is other name for the other name for this theoretical arch is line of thrust. Thrust in the sense compression. So line of compression or network of lines of compression. All you can call it in many ways. Right. Select a point A. Select a point A. So we have already got this point selected A. So select a point A on line of thrust. Draw a vertical line which will intersect the actual arch. So this is the vertical line drawn. So which is intersecting this actual arch here. Okay, now let us see. N cos theta is the horizontal component of thrust N. So let us see the compressive force acting in this region is N. Okay, right. Now if you take a section here, if you take a section and separate this part and this part, we will redraw this portion. So this is where the line is taken, and this is the section that is taken. Right. So this is the normal force, the normal to this section, and you will have two components that you are very well aware of, the force components from your engineering mechanics study. So this will be the horizontal component, this will be the vertical component. Right, now we will talk about this N cos theta. So this being theta, so this component is N cos theta, is the horizontal component of the thrust. Okay, now bending moment uh, at this point, bending moment at this is a point, bending moment at this point is nothing but this force. So you have horizontal component, vertical component here of this compression. So vertical component pass through this point. There is no point in taking that force into the bending moment calculation. Distance is 0. So horizontal component multiplied by the perpendicular distance is E. That is what is written here. N cos theta into E. Right? Now, next statement, as n cos theta is constant throughout the arch. Why n cos theta is constant? What is the reason? Because vertical force, I mean to say vertical reaction is going to change because you have gravity loads acting on this arch. So you take a section here. What do you write? You write sum of all vertical forces to the left or to the right. That is what you count. Okay, so if you take a section here, all the forces acting to the left, vertical forces, will come into picture. So likewise, if there are gravity loads acting on the arch, only the vertical load will change along the arch, whereas horizontal, there won't be any horizontal loads on this arch. So only one horizontal force acting is the horizontal reaction acting at springing points. Okay, so this is these are the two horizontal forces, horizontal reactions in the other way, because you are applying the vertical loads. So this is the horizontal force or reaction developed at the two supports. So you take a section anywhere on the arch, the h is going to be the same value. Okay, so that is nothing but equal to n cos theta always. So this should balance this one. So h should balance this one, or this should balance this one. So as there are no horizontal forces acting on the arch, because the loads that are acting on the arch are taken as gravity loads, which are always vertically downward, no horizontal force externally acting on the arch, so only prevailing horizontal forces are the support reactions, and they are equal in value, because sigma fx 0 they should satisfy. And if you take a section anywhere in the arch, sum of all forces, all horizontal forces to the left will come to be only the horizontal reaction at this support. So likewise, you have n cos theta, which is always equal to h. So that is why this statement is given. N cos theta is constant throughout the arch, means wherever you take section anywhere in the arch, always n cos theta is equal to h only. So n cos theta, when it becomes constant, then you can write, by removing this equality, bending moment is proportional to E. So in the other way, we will to better understand, we will come like this. So F is proportional to A. This is a well-known theorem that you know already. So force is proportional to acceleration. So what do you write? By removing proportionality, F is equal to, we write MA. This is what we write. Okay, so now here you are relating force and acceleration. Similarly, we will write bending moment relating to E, nothing but the vertical intercept. So bending moment is proportional to vertical intercept is proved as said in the statement. This is clearly what is meant by Eddy's theorem and how do you prove it. Okay.